In 2017, a traveler from another star broke every rule we thought we understood about space rocks. This slender, needle-shaped object was racing through space at over 50 miles per second. Yet somehow, it began accelerating in ways that should have been impossible. No glowing tail, no icy trail, just a dark shard tumbling through our solar system faster than anything we had ever seen before. But that was only the beginning. You're about to witness how this first mysterious visitor inspired us to build the most advanced skywatching network ever created. And how, in July 2025, we discovered something that made that original visitor seem almost ordinary. Like and subscribe to join us on this cosmic detective story. Prepare yourselves. We begin. October 19th, 2017, changed everything we thought we knew about visitors from deep space. Astronomer Robert Verick was doing what astronomers do on every clear night in Maui, scanning telescope images for tiny dots moving among the stars. The Pan-STARRS telescope had captured something unusual. At first glance, it looked like just another harmless space rock drifting through our cosmic neighborhood. Then, the measurements came in. This object was moving at 196,000 miles per hour. That's 54 miles every single second. To put that in perspective, imagine a bullet traveling from New York to Los Angeles in just over 1 minute. That speed revealed something astonishing. This visitor wasn't from our solar system at all. It came from another star. Nothing bound to our sun moves that fast. Our asteroids and comets cruise along at a calm 12 miles per second on average. This newcomer was flying nearly 5 times faster. That meant it had been traveling through the vast emptiness between stars for millions, maybe hundreds of millions, of years before it stumbled into our solar system. We gave it a Hawaiian name, fitting for the first messenger from the stars, a word meaning scout or messenger arriving first from afar, but speed was only the start of its strangeness. As telescopes around the world tracked the object, astronomers noticed something that made no sense. It was tumbling end over end like a spinning baton in space, and its brightness changed dramatically every 7.5 hours. That told us its shape was unlike anything we'd ever seen before. Most asteroids are roughly round, lumpy, potato-shaped worlds. Most comets are icy snowballs with uneven, compact forms. But this visitor was something entirely different. The brightness shifts suggested it was about 10 times longer than it was wide. Picture a skyscraper lying on its side, spinning through space. No known asteroid or comet in our solar system has such an extreme shape. It looked like a cosmic pencil, or perhaps, as some whispered, something built, not born. An alien craft? That idea sounded far-fetched, but the data refused to be ignored. There it was, a dark shard of rock or metal tumbling through our solar system, shaped by forces we couldn't yet explain. And as if that weren't strange enough, there was one more puzzle waiting. Something that would confuse scientists for years and ignite theories ranging from the plausible to the extraordinary. The mystery was only beginning to unfold. What came next would challenge everything we thought we knew about objects from other star systems. Because compared to what astronomers would soon discover about its motion, the shape was just the warm-up act. High on the summit of Haleakala, the Pan-STARRS telescope stands like a cosmic lighthouse, sweeping the Hawaiian skies for anything that moves. Every night, this automated hunter captures countless images of the heavens, searching for faint specks that drift against the stillness of distant stars. Most nights, it spots the usual suspects: main belt asteroids slowly orbiting between Mars and Jupiter, an occasional comet from the outer solar system, or a near-Earth asteroid that deserves a closer look. But that night, October 19th, was different. Very different. The computer flagged something that made astronomers pause mid-sip and stare in disbelief. On their screens appeared a faint, moving dot gliding across the starfield. At first glance, nothing about its motion seemed unusual. Space rocks move, that's what they do. But once astronomers calculated its trajectory, the realization hit hard. They were looking at something that shouldn't exist. This object wasn't orbiting our sun. It was passing through our solar system, a true interstellar traveler, never to return. When scientists traced its path backward, it pointed toward the bright star Vega in the constellation Lyra. But here's where the mystery deepened. The journey to reach us took roughly 300,000 years, and in that time, Vega had already moved to a completely different part of the sky. That meant this visitor had been drifting through the void of interstellar space long before modern humans even existed. It had wandered the galaxy while our ancestors were just beginning to craft tools and paint on cave walls. The Discovery team knew instantly this was something historic. For decades, astronomers had theorized that interstellar objects must exist. After all, other star systems should occasionally fling their own asteroids and comets into the galaxy, just as ours does. When a massive planet exerts its gravity on a smaller body, it can hurl that object into space at escape velocity, sending it on a million-year journey between the stars. The math said these wanderers were out there, but actually, finding one was like searching for a single grain of sand on every beach on Earth. And yet, they had found it. But discovery was only the beginning. As telescopes around the world began tracking this cosmic drifter, new mysteries emerged. Its brightness told a story unlike anything astronomers had ever seen. The way sunlight reflected off its surface revealed scars of a journey that spanned unimaginable distances and times. This object had been battered for hundreds of millions of years by high-energy particles. Radiation from exploding stars and violent cosmic storms. That relentless exposure had slowly stained its surface a deep rusty red, like iron weathered by eternity itself. The color told a story of age, ancient beyond measure. This traveler had likely been drifting between stars since before our own solar system had even settled into shape. While Earth was still being pummeled by asteroids during the violent early days 4 billion years ago, this object may have already been roaming the galaxy, carrying secrets from a long-lost homeworld. Yet even as astronomers celebrated the first confirmed interstellar visitor, they didn't realize the biggest mystery was still waiting. Something about this object would soon challenge every explanation they had. As the observations continued, the brightness data became even stranger. As it spun through space, the reflected light flickered wildly, as if a cosmic lighthouse beam was sweeping across the sky. But instead of a steady pulse, this beacon flashed unpredictably every few hours. Its brightness changed by more than 2.5 times as it rotated. That kind of variation meant one thing. This was no ordinary space rock. Most asteroids are roughly spherical, like lumpy cosmic potatoes. Even the most stretched asteroids in our solar system rarely measure more than 3 times longer than they are wide. But this visitor was different. The data revealed an object at least 10 times longer than its width. Imagine a skyscraper laid on its side, tumbling end over end through the dark vacuum of space. The shape was so extreme that some scientists began to wonder, was it even whole? Maybe it was a fragment, a sliver of something much larger, shattered long ago by a violent cosmic collision. Perhaps 2 asteroids had slammed together in another star system, and this needle-shaped shard had been flung into interstellar space by that ancient explosion. But others proposed something even stranger. What if it wasn't rock at all? What if it was made of ice? In the freezing depths between stars, exotic ices can form that could never survive near a sun. Perhaps this visitor was sculpted from hydrogen ice, born deep within a molecular cloud, a cradle of stars and planets where temperatures plunge to unimaginable lows. Under those extreme conditions, matter takes on forms unseen in our solar system. The hydrogen ice theory could explain its bizarre shape. As it approached our sun, its outer layers might have slowly evaporated away, reshaping it into the elongated figure astronomers observed. Like a cosmic sculpture carved by sunlight itself, this interstellar iceberg may have reshaped and refined its form as it drifted closer to our star. A silent relic, sculpted by starlight, carrying the whispers of another world. The process could, in theory, reshape an ordinary round object into the elongated needle form that left astronomers baffled. Yet even this exotic explanation struggled to hold up. The object was simply too dark, too small, and far too solid to be made entirely of ice. Its surface reflected light like stone or metal, not the bright, glossy sheen expected from frozen material. And its deep red hue suggested a surface weathered by countless ages of cosmic radiation. Its chemistry slowly altered in ways that no ice could have survived. So some researchers dared to ask the most radical question of all. What if this wasn't natural? The shape was unlike any asteroid or comet ever observed. Its long, perfectly balanced form almost looked engineered. Could it be a fragment of alien technology? Debris from a civilization orbiting another star? Perhaps even a probe, designed for purposes we couldn't begin to imagine. Most scientists remained skeptical of that extraordinary idea, but none could deny that this object defied every expectation of what a natural space rock should be. And as strange as its shape seemed, that was only the beginning. its motion told an even stranger story. This interstellar traveler wasn't just fast, it was impossibly fast. Clocking in at over 196,000 miles per hour, it was moving nearly 5 times quicker than the average asteroid or comet in our solar system. To picture that, imagine standing beside a highway where traffic hums by at 60 miles an hour, and then something screams past at 300. That's the cosmic equivalent of what astronomers were witnessing. The speed alone proved its alien origin. Nothing bound to our sun could ever achieve such velocity naturally. Even our most advanced spacecraft, after slingshotting around multiple planets, barely reach 40 miles per second. Yet this visitor was sailing through space at more than 50, carrying the kinetic energy of a million-year voyage between the stars. But speed creates mysteries of its own. Objects moving that fast encounter subtle forces that slower travelers never feel. The thin gas and dust that fill the void between stars, the interstellar medium, act like a faint cosmic headwind. Over eons, that drag should gradually slow an object down. But this traveler had lost none of its momentum, suggesting its journey hadn't lasted as long as astronomers once believed. Its path added another twist. When scientists traced the trajectory backward, they realized it hadn't traveled in a perfectly straight line. Something, somewhere, had nudged its course during its ancient voyage. Perhaps it had passed near another star, its gravity bending the object's path like a slingshot. Or maybe it had drifted through a massive cloud of gas and dust, the kind that holds enough raw material to form thousands of new suns. Whatever had shaped its route, one thing was certain: time was running out. At that astonishing speed, astronomers had only a brief window to study it. Unlike comets and asteroids that linger for months or years, this interstellar wanderer was already on its way out. By the time it was discovered, it had passed its closest point to the sun and was now racing away into the darkness, fading with every passing night. Telescopes across the world scrambled to capture every last bit of data. Each observation, each measurement, could reveal a clue about the nature of this mysterious visitor and the distant system it once called home. The pressure sparked one of the most rapid global collaborations in astronomy's history. From Hawaii to Chile, from South Africa to Spain, observatories united for a single goal: to understand this cosmic intruder before it vanished forever. Radio telescopes listened intently for any unnatural signals, hoping for even a whisper of artificial origin. Infrared detectors searched for traces of heat that might betray its composition. But even as this unprecedented investigation unfolded, the object had one last surprise in store, one that would shake the very foundations of celestial physics. In June 2018, Marco Micheli and his team at the European Space Agency made an announcement that sent shockwaves through the scientific world. The interstellar visitor was not following the path gravity predicted. As it moved away from the sun, it began to drift, ever so slightly, off its calculated course. It was accelerating. The change was tiny, almost imperceptible, like a marble rolling across a smooth table, suddenly nudged forward by an invisible breeze. The force was delicate, about what you'd feel if someone gently blew across your face. But in space, where nothing resists motion, even a whisper of acceleration is monumental. In a universe ruled by gravity, planets, asteroids, and comets all obey its pull. But this object? It seemed to be following its own rules. At first, astronomers thought the cause might be outgassing, a well-known process in which frozen material on a comet's surface turns directly into gas, acting like a tiny rocket engine that pushes the comet away from the sun. It's common, predictable, and easily explained, except this object showed no trace of it. There was no bright halo of gas, no shimmering tail streaming into space, no visible activity of any kind. Telescopes saw only a dark, solid fragment tumbling silently through the void. And yet somehow, it was accelerating exactly as if it were an active comet. When scientists calculated how much material would need to vent to cause that motion, the numbers made no sense. A comet producing that level of thrust would glow with a massive coma, its tail stretching thousands of miles, visible even through small backyard telescopes. Instead, there was nothing. No glow, no tail, no explanation. And so, the mystery deepened, forcing science itself to question whether this was truly a rock from the stars, or something far beyond what we've ever imagined. Perhaps the object was ejecting material that was simply too dark to see. Particles made of pure carbon that absorbed light instead of reflecting it. Or maybe it was venting gas in narrow jets, aimed directly away from Earth, making the outgassing invisible to our telescopes. Some scientists proposed an even stranger idea, that the acceleration was caused by sunlight itself. The pressure of light reflecting off the surface could provide a tiny but steady push. Normally, this radiation pressure is far too weak to matter compared to gravity. But if the object was unusually light or thin, even sunlight could move it. This led to the most controversial theory yet. Perhaps this mysterious visitor was not a comet at all, but something far more extraordinary. Every comet we've ever studied follows a predictable script. As it approaches the sun, the heat causes frozen gases to sublimate, releasing jets of vapor and dust. These particles form a glowing halo called a coma, and solar wind stretches that material into a magnificent tail that can span millions of miles across the sky. But this interstellar visitor broke every rule. It showed the telltale acceleration of a comet, yet no coma, no tail, and no glowing dust. The most powerful telescopes on Earth and in space searched for any hint of gas or heat and found nothing. The Spitzer Space Telescope, capable of detecting the faint warmth of dust from billions of miles away, stared at the object for hours. If it were shedding even the slightest amount of material, Spitzer would have seen it, but it didn't. The object remained cold, dark, and eerily silent against the backdrop of the stars. This realization forced scientists to confront an unsettling question. How could something accelerate in space without releasing anything at all? Some proposed it was venting gas through hidden cracks, perfectly aligned away from our view. Others suggested the expelled material was so dark, like pure carbon, that it escaped detection. Yet, the boldest theory claimed it wasn't a comet in any sense we understood. Its motion, shape, and acceleration hinted at something entirely different, perhaps even artificial. Alan Jackson and Stephen Desch at Arizona State University proposed a natural explanation. The object might be a fragment of frozen nitrogen from a Pluto-like world in another solar system. As nitrogen ice sublimated, it could produce thrust without creating a visible tail. This would explain both its acceleration and its strange, elongated shape, carved by uneven erosion as it passed near our sun. Other scientists offered alternative possibilities. Some suggested it could be made of hydrogen ice, an extremely rare material that could vaporize invisibly when heated. Others imagined it as a fragile, porous structure, a fractal cloud of dust and ice so light that even sunlight could push it, like a cosmic balloon drifting through space. And then came the most controversial idea of all. Harvard astrophysicist Avi Loeb proposed that this object might not be a natural rock or ice fragment at all, but an artificial structure. According to his calculations, the way it accelerated matched perfectly with what would happen if it were a light sail, a thin, reflective sheet designed to harness sunlight for propulsion. It was a technology humans had only begun to dream about, but one that an advanced extraterrestrial civilization could have mastered long ago. The light sail hypothesis suggested something astonishing, that this mysterious visitor might be a piece of alien technology. Perhaps it was a functioning probe sent to explore our solar system, or debris from a long-forgotten cosmic engineering project. While Avi Loeb acknowledged that natural explanations were far more likely, he argued that true science must consider every possibility that fits the evidence, no matter how extraordinary it may seem. His claim ignited fierce debate within the scientific community, exposing deep divisions about how to approach unexplained phenomena. But as theories clashed, a new discovery would emerge, one that offered the most compelling and elegant solution yet. In March 2023, Jennifer Bergner at UC Berkeley, working with Darryl Seligman of Cornell University, uncovered a breakthrough that completely changed our understanding of this interstellar traveler. They discovered that the answer might lie not in alien technology, but in the quiet, invisible chemistry of ordinary ice drifting through space for millions of years. Cosmic radiation constantly bombards objects traveling between stars. Over time, high-energy particles from exploding supernovas strike water ice, splitting the molecules into hydrogen and oxygen, just like in a particle accelerator. But in the freezing vacuum of space, the hydrogen can't escape. Instead, it becomes trapped within the ice, forming countless tiny bubbles, like air pockets frozen in glass. Over millions of years, This process could transform up to 30% of the ice into trapped hydrogen gas. The result? A kind of natural hydrogen battery, quietly storing energy from cosmic radiation across eons. Then, as the object approached our sun, everything changed. The warming caused the ice structure to shift and collapse, squeezing those microscopic gas pockets and releasing the hydrogen into space. A gentle but steady jet of thrust, like air escaping from a balloon. This invisible hydrogen outgassing would act as a natural rocket engine, perfectly explaining the strange acceleration astronomers observed. And because hydrogen is almost completely transparent, no telescopes on Earth could detect it. Suddenly, the puzzle made sense. The acceleration could be real, yet invisible. A natural mechanism, not alien engineering, could explain it all. Bergner's model tied everything together beautifully. It explained the gentle acceleration, the lack of a visible tail, and even the direction of the motion, all consistent with hydrogen escaping away from the sun. It required no exotic materials, no artificial constructs, just the long-term chemistry of ice exposed to cosmic radiation. But this discovery revealed something else. Something unsettling. The first interstellar visitor had shown us that we were nearly blind to small objects entering our solar system. Existing asteroid surveys like Pan-STARRS were excellent at detecting large bodies months or years before impact, but smaller ones could slip by unnoticed until it was too late. In 2013, the Chelyabinsk meteor proved that danger all too clearly. A rock barely 60 feet wide exploded over Russia with the power of 30 Hiroshima bombs, injuring over 1,000 people and damaging thousands of buildings, and it arrived completely undetected. The reason? It came from the direction of the sun, a blind spot where our telescopes cannot look. To fix this vulnerability, Larry Deno and his team at the University of Hawaii proposed a bold new system, one that could scan the entire sky every night, looking for anything that moved against the stars. Their creation would become known as ATLAS, the Asteroid Terrestrial Impact Last Alert System. Its mission was simple but critical: to be humanity's final warning. ATLAS was designed to detect a 60-foot asteroid several days before impact, and a 300-foot one several weeks ahead, enough time to sound the alarm. Building it was no small feat. Scanning the entire sky nightly required telescopes with enormous fields of view and cameras sensitive enough to detect objects 100,000 times fainter than what the human eye can see. NASA funded the project in 2013, and 2 telescopes were built in Hawaii, one on Haleakala and another on Mauna Loa. Their separation allowed parallax measurements and backup against bad weather. By 2017, both were fully operational, collecting over 250 gigabytes of data every single night. Automated systems analyzed each image in real time, sifting through the digital noise of the cosmos for faint trails of motion, like detectives scanning the heavens for cosmic intruders. But there was still one major blind spot: the southern hemisphere. To cover the entire planet, NASA funded 2 more ATLAS telescopes in Chile and South Africa. By early 2022, humanity had achieved something remarkable. For the first time in history, 4 robotic telescopes, spread across the Earth, worked together as one global planetary defense network. Each telescope, though modest in size with 20-inch mirrors, could image a patch of sky large enough to fit 15 full moons side by side. Every night, they photographed a quarter of the entire sky, capturing more than 110 million pixels per image, enough data to fill dozens of smartphones in a single night. Together, this worldwide network of eyes could watch every dark corner of the sky, every 24 hours, giving humanity the power to see what was once invisible. The global positioning of these robotic sentinels creates overlapping coverage, ensuring that no part of the sky is ever left unwatched. When it's daytime in Hawaii, the telescopes in South Africa and Chile continue the vigil. Even when storms or volcanic eruptions strike one site, the others maintain their silent watch among the stars. The 120-degree spacing between each station means that even small asteroids, visible for only a day or two, cannot escape detection. Every clear night, each telescope follows the same precise routine. The visible sky is divided into 1,500 patches, like a vast cosmic checkerboard. The telescope captures 4 30-second exposures of each patch, spaced 10 minutes apart. This pattern allows the computer systems to identify anything that moves between images, separating true celestial travelers from cosmic rays, satellites, and distant quasars. All data is processed in real time. Powerful computers analyze every image the moment it's captured, calculating orbits and identifying motion. Each discovery is instantly compared against databases of known asteroids and comets, flagging only genuine new objects for human review. Within hours, confirmed discoveries are reported to the Minor Planet Center, the International Clearinghouse for Asteroid and Comet Tracking. This automated detection network has revolutionized humanity's ability to spot cosmic threats before they reach us. Since becoming fully operational, Atlas has discovered over 700 near-Earth asteroids and 66 comets. It has even detected 2 small asteroids that later impacted Earth, proving its ability to provide crucial early warnings of incoming dangers. But Atlas's power goes far beyond planetary defense. By scanning the entire sky multiple times every night, it has become one of the most productive systems for discovering supernovae, variable stars, and countless other cosmic events that change the night sky. Then, in July 2025, the network made a discovery that would forever reshape our understanding of visitors from other star systems. July 1st, 2025. It began like any other night at the Atlas station high in the Chilean Andes. As the sun set behind the mountains, the robotic telescope at El Source Observatory came to life. Its automated systems powered up, sensors cooled, and the wide-field camera began its nightly ritual of capturing the southern sky, one patch at a time. Each image was instantly processed by advanced algorithms, searching for faint, slow-moving points of light against the star-filled background. At first, everything appeared routine. The software flagged a faint object drifting slowly across the field, the kind of distant asteroid Atlas had detected countless times before. Preliminary calculations showed nothing unusual, just another small space rock following a predictable orbit around the sun. The system logged the find and prepared to move on. But as more data arrived throughout the night, something began to stand out. The object's path didn't match the elliptical orbit of typical solar system bodies. Instead, its trajectory revealed a hyperbolic curve, the unmistakable signature of something not bound by the sun's gravity. This was the same kind of orbit traced by the mysterious first interstellar visitor years earlier. Whatever this was, it had come from beyond our solar system. Immediate alerts were sent across the global astronomical network. Within hours, telescopes around the world turned their gaze toward the new target, racing to capture observations before it slipped away into the dark. The Gemini North Telescope in Hawaii, the Canada-France-Hawaii Telescope, and the Lowell Discovery Telescope in Arizona all joined the effort. But unlike the first interstellar visitor, this one revealed its nature almost instantly. Through powerful telescopes, astronomers saw a glowing, diffuse cloud surrounding a bright core, a coma. This was no silent, inert rock. This was an active comet, venting gas and dust as it approached the sun. Its shimmering tail told the story clearly. Ice on its surface was vaporizing into space, just like the comets native to our solar system. Yet this one carried chemical fingerprints from a distant star system, matter forged around another sun, billions of years and light years away. Veteran comet hunters David Jewett and Jane Liu confirmed the activity using the Nordic Optical Telescope. Their data showed the coma expanding, glowing brighter each night as the comet drew closer to the sun. For the first time in history, humanity was witnessing an active interstellar comet, performing the same ancient dance our own comets have traced for eons. Excitement swept through the scientific world. Unlike the enigmatic first visitor, this object promised to reveal its secrets through known, observable processes. Spectroscopy could uncover its chemical composition. Imaging could track its evolution in real time. But astronomers knew time was short. Like all interstellar travelers, it would soon vanish back into the deep. On July the 2nd, the official announcement came. The Minor Planet Center, the international authority for cataloging small bodies, confirmed the discovery. The object received its formal name, C2025. N1-3I, the third confirmed interstellar object ever detected. The first had been the mysterious elongated traveler of 2017. The second, the faint, icy comet that followed years later. And now, the third visitor, brighter, more active, and more revealing than any that came before. The second interstellar visitor had been Comet Borisov, discovered in 2019, a wanderer that behaved just like any normal comet, except for one astonishing fact: it came from another star system. But this new discovery was something entirely different. For the first time in history, astronomers had detected an active interstellar comet while it was still approaching the Sun, not after it had already begun to leave our solar system behind. This timing changed everything. It meant scientists had months to study its behavior, to watch its activity increase, to see its transformation unfold in real time, instead of racing against the clock as they had with the previous visitors. Soon after the announcement, researchers began digging through archived telescope data from around the world, and what they found was stunning. The Vera Rubin Observatory had actually captured images of this object days before the Atlas discovery, during its testing phase in late June. Those images had simply not been processed yet. Even earlier, NASA's Transiting Exoplanet Survey satellite, TESS, had unknowingly recorded the comet as far back as May 7th, when it was still more than 6 times farther from the Sun than Earth. These early observations revealed something remarkable. The comet had been active for far longer than anyone imagined. Even at such enormous distances, where sunlight is too weak to melt water ice, the comet was already venting gas into space. That meant something else was fueling it. Far more volatile materials like carbon monoxide or carbon dioxide, which can sublimate at much colder temperatures. This wasn't just a frozen rock. It was a cosmic time capsule powered by exotic chemistry from another world. Trajectory analysis confirmed what astronomers had begun to suspect. This object didn't belong here. When its path was traced backward through time, it clearly originated from beyond our solar system, arriving from the direction of the constellation Sagittarius, where the dense, star-packed heart of our galaxy lies. It had been traveling for millions of years, drifting through interstellar space before crossing paths with the Sun's gravity. And unlike the mysterious first visitor, whose acceleration had baffled scientists, this new comet's motion followed the laws of physics perfectly. The gentle thrust of gas escaping from its surface explained every change in its trajectory. No need for speculation, no exotic theories, just pure science at work. The discovery was also a triumph for the global Atlas network. By scanning the entire sky every night, Atlas had done exactly what it was designed to do: find fast-moving, faint objects early, long before they vanished into the void. Older detection systems, focused mainly on large asteroid threats, would have completely missed this southern sky traveler. Within days of the discovery, the Hubble Space Telescope locked onto the comet. What it revealed took humanity's breath away. For the first time ever, we were seeing an active comet from another star system, up close, in detail, performing the same cosmic ballet. Our own comets have danced for billions of years. Hubble's images showed a glowing coma, stretching over 8,000 miles across, a shimmering cloud of gas and dust surrounding a tiny, brilliant nucleus. Spectral data revealed familiar substances: water vapor, carbon monoxide, and carbon dioxide, the same materials that drive comets in our own solar system. But hidden within that familiarity were subtle, telling differences, signs of its alien origin. The dust particles within the coma were larger on average than those found in typical comets. Tiny grains about 1 micron wide raced outward at nearly 70 feet per second, while larger particles moved more slowly, barely drifting at 6 feet per second. These properties told a deeper story: that this comet was born in a different kind of planetary system, one where the chemistry and temperature during formation were unlike anything in our own. The abundance of heavy elements hinted that its home star system may have been richer in metals, a stellar nursery forged in a different era of the galaxy. As July turned into August, telescopes continued to track its slow, graceful approach toward the Sun. The Canada-France-Hawaii telescope captured the first faint images of a tail forming, a thin, luminous streamer pointing away from the Sun, sculpted by the relentless pressure of the solar wind. For the first time in human history, Astronomers were watching an interstellar comet grow its full display, coma and tail, in real time. And this tail wasn't just beautiful, it was a clue. Its color, brightness, and motion revealed what elements it contained and how the solar wind was shaping it. Every molecule left behind a unique spectral fingerprint, allowing scientists to decode its chemistry, atom by atom. Soon, telescopes around the globe joined the campaign, from Hawaii to the Canary Islands to Chile, forming the largest coordinated observation effort ever mounted for an interstellar visitor at the Gran Telescopio Canarias, the world's largest optical telescope. Astronomers measured the comet's rotation, one full spin every 16.75 hours. It was almost identical to many native comets, a sign that despite its ancient interstellar journey, this traveler still carried the same physical soul as those born around our own sun. This was not just another comet, it was a messenger, a fragment of another solar system, crossing billions of miles to tell us the story of where it came from, and perhaps to remind us how much of the universe we have yet to understand. The European Southern Observatory tracked how the comet's brightness changed as different sides of its icy nucleus turned toward the sunlight. Over time, those variations began to fade, a sign that the entire surface was waking up. Frozen regions that had slept for eons were now alive, glowing as the comet drew closer to the sun. Unlike the mysterious first interstellar visitor, this new cosmic wanderer behaved exactly as astronomers expected. Every observation fit perfectly with the known physics of comets in our own solar system. But hidden in that very normal behavior were extraordinary clues that could reshape how we understand the birth of planetary systems across the galaxy. The difference between the two interstellar visitors is staggering. The first one, that strange cigar-shaped object, was estimated to be anywhere between 300 and 3,000 feet long. Imagine a skyscraper spinning through the void, perhaps as tall as the Eiffel Tower, stretched into a cosmic needle. It was barely large enough to be detected before it vanished into the black. This new comet, however, is a giant by comparison. Early measurements suggest a nucleus several miles wide, roughly 100 times more massive than its predecessor. Think of it as the difference between a school bus and a small city. That massive scale gives astronomers a far greater opportunity to study, observe, and decode its secrets. Its vast size also explains the spectacular show we see now. With more surface area and far more ice exposed to sunlight, the comet produces an enormous glowing coma and tail, bright enough for telescopes across the world to capture in detail. The first visitor, even if it carried ice, was simply too small to create such visible activity. Size determines not only brightness, but also longevity. The first interstellar object faded from sight within just a few months. This one will stay visible for many more, giving scientists precious time to explore its structure and chemistry. That difference in mass even affects how sunlight itself interacts with it. The smaller object was easily pushed around by solar radiation, magnetic fields, and the solar wind, subtle forces that could change its path. But this larger comet is governed almost entirely by gravity, moving along a stable, predictable course. Its very existence tells us something remarkable about the system it came from. Large comets require vast reservoirs of ice and dust, meaning the star that birthed this traveler likely had a massive debris disk, much like our early solar system. If such comets are this common, it suggests that planetary systems like ours may be scattered all across the galaxy, and there's another secret locked within its size: protection. The thick layers of ice and rock shield its inner core from cosmic radiation. That means much of its interior remains exactly as it was when it first formed, a frozen time capsule from another star's nursery. Studying its light could reveal materials almost untouched since the dawn of its creation. But this discovery also raises a haunting question. Are these the rare few interstellar objects we've managed to detect, or just a tiny glimpse of a vast unseen population drifting between the stars? When the Atlas Observatory first detected this comet, it was tearing through space at a 137,000 miles per hour. That's 38 miles every second, fast enough to cross the entire United States in less than 2.5 minutes. Imagine standing by a highway where cars rush past at 70 miles per hour. This interstellar traveler would blaze by nearly 2,000 times faster, crossing from New York to Los Angeles in the time it takes to make a cup of coffee. But in space, speed behaves differently. As it falls deeper into the sun's gravity well, it accelerates, like a marble racing down a slope. By October, when it reaches its closest point to the sun, it will be moving at over 160,000 miles per hour. This motion reveals the incredible power of our star. The sun's gravity, reaching across billions of miles, bends the comet's straight interstellar path into a sweeping curve, a cosmic slingshot that will hurl it back into deep space. Tracking an object like this isn't easy. Most comets crawl slowly across the sky, easy for telescopes to follow. But this one is a cosmic bullet, moving so fast that astronomers must constantly readjust their instruments just to keep it in view. Long exposures risk blurring it into streaks of light, forcing scientists to balance precision with speed. And they know, once it's gone forever. Unlike the comets that revisit every few years, this traveler will pass through our solar system just once, never to return. Its velocity also reveals something profound about our galaxy's motion. Our entire solar system races around the Milky Way at about 500,000 miles per hour. This comet, however, comes from a completely different stellar neighborhood, carrying its own momentum through the galactic sea. When the two paths intersect, we get this rare chance to witness a true interstellar encounter. And when astronomers point their instruments at that glowing coma, they're doing more than just watching a comet. They're studying the chemistry of another world. Every photon that reflects off its surface carries ancient information, light that has traveled for millions of years. Within those wavelengths lies a kind of cosmic DNA, the chemical fingerprint of a planetary system far beyond our own. The first spectroscopic readings from this interstellar comet revealed both the familiar and the unexpected. Right away, astronomers detected water vapor, clear proof that H2O ice forms around other stars, just as it does here in our own solar system. Carbon monoxide and carbon dioxide appeared in the exact ratios they'd expect, confirming that the chemistry of comet formation seems to follow the same universal rules, no matter where in the galaxy it happens. But then, the subtle differences began to appear, hidden within the isotope ratios. Isotopes are simply versions of the same element, but with different numbers of neutrons in their nuclei. And those differences tell a story. The ratio of oxygen isotopes, for example, depends on the precise conditions that existed when the comet formed. Things like temperature, pressure, and the chemical makeup of the surrounding gas cloud. These tiny variations act like a cosmic birth certificate, capturing the environmental fingerprint of the comet's birthplace billions of years ago. One particular measurement, the ratio of deuterium to hydrogen in its water vapor, offers even deeper insight. Deuterium is heavy hydrogen, carrying an extra neutron. The amount of it that becomes locked inside water ice depends on how cold or warm the environment was during formation. By studying this ratio, astronomers can tell whether the comet formed in the warm inner regions of its home system or in the cold, distant outskirts. And the evidence is clear. This interstellar traveler was born in a frigid outer realm, under conditions strikingly similar to those found in our own Kuiper belt, far beyond Neptune. That resemblance suggests something extraordinary. The processes that build planets and comets may be remarkably consistent across the galaxy. Still, not everything matched our expectations. Some trace metals in the comet's dust were slightly different from what we see in solar system comets. That hint points to a parent star with a different chemical makeup, perhaps one enriched by earlier generations of stellar explosions. Those ancient blasts seeded its nebula with heavier elements, which later became part of its planets and comets. And then came the most tantalizing discovery of all: organic compounds. Within the comet's glowing coma, astronomers found not only simple molecules like formaldehyde and methanol, but signs of more complex carbon-based chemistry. These molecules may hold the fingerprints of chemical evolution that took place in another star's nursery, a glimpse into the early steps that might one day lead to life elsewhere. For the first time in human history, we're studying unaltered material from another planetary system without leaving our own. And the comet's brilliant tail tells an even deeper story. What looks like a single glowing streamer is actually two distinct tails, each revealing a different aspect of its nature. The ion tail, made of charged gas molecules, stretches straight away from the sun like a cosmic windsock, pushed by the solar wind. The dust tail, however, curves gently, shaped by the balance between solar radiation and the comet's own motion. The ion tail acts as a live chemical laboratory. As sunlight bombards the gas, ultraviolet rays strip away electrons, creating glowing ions that shine in vivid colors. Sodium glows yellow, carbon monoxide shines blue, and water ions emit a blue-green light. Each hue reveals the elements at play, their quantities, and their interactions in real time. The dust tail tells a more ancient story. The way it scatters sunlight reveals the size and structure of its grains. Tiny, frozen relics from the nebula that birthed it. Unlike gas, these solid particles preserve their original chemistry, untouched since the day they formed billions of years ago. Even the ratio between gas and dust tells astronomers how and where the comet was born. Comets that form close to their parent star tend to be dusty and dry. Those born in the cold outer zones are rich in ice, releasing vast plumes of gas when warmed by starlight. And this interstellar comet, it shows the same balance of gas and dust seen in the long-period comets that hail from our own Oort cloud. Another sign that it, too, was born in a distant, icy frontier, its chemistry, its motion, its glow. Everything about this cosmic visitor whispers a familiar truth across light years of space. We are not unique. The same processes that shaped our solar system are at work across the galaxy, building worlds, forming comets, and carrying the building blocks of life from one star to the next. The comet's magnificent tail holds more than beauty. It's a messenger from another world, carrying clues about the environment of its parent star. By studying the dust streaming behind it, astronomers can learn how magnetic fields in other star systems once shaped the birth of planets. Different stellar magnetic strengths influence how dust grains stick together, clump, and grow into larger bodies. The sizes and patterns of those grains, now drifting in this comet's tail, preserve the ancient record of those forces, frozen in time for billions of years. As the comet continues to draw closer to the sun, its tail will grow longer, brighter, and far more dramatic. Solar heat will begin to vaporize the deeper, untouched layers of ice beneath its surface, exposing materials that have been locked away since the very dawn of its creation. These pristine substances could hold organic molecules or mineral structures that tell us exactly what chemical conditions were like in a distant stellar nursery long ago. Every stage of the tail's transformation helps astronomers model how the comet has changed. During its endless journey through interstellar space, cosmic radiation gradually reshapes surface materials, but the interior remains preserved, a frozen archive of history. As sunlight warms it layer by layer, scientists can effectively peel back time itself, uncovering evidence from different eras in the comet's existence. This moment marks something truly extraordinary. Humanity's first chance to watch an active interstellar comet evolve in real time. Never before have we been able to witness such dynamic behavior from an object that was born around another star. Tracking. This cosmic traveler is no small feat. To put its speed into perspective, the fastest sniper bullet travels at about 3,000 feet per second. This interstellar comet, over 200,000 feet per second, that's about 67 times faster than a speeding bullet. Yet instead of streaking straight ahead for seconds, it curves gracefully through space for months, demanding constant precision adjustments from every telescope aimed its way. Modern observatories rely on sophisticated computer-controlled mounts that calculate the comet's predicted position thousands of times per second, adjusting continuously to counter both Earth's rotation and the comet's blistering motion. For ordinary asteroids or comets, this tracking is routine, but for interstellar objects it pushes technology to its absolute limits, and even finding where it will appear next isn't simple. Objects born in our solar system follow predictable elliptical orbits. Interstellar visitors, however, travel along hyperbolic paths, open-ended trajectories that can be altered by the faintest jets of gas erupting from their nuclei. Each burst of activity slightly shifts their orbit, forcing scientists to recalculate its position night after night. To overcome this, observatories across the globe work together in perfect synchrony. When the comet sets below the horizon in one hemisphere, telescopes on the opposite side of the planet take over. This global relay of observation ensures the comet is never lost, even as Earth spins beneath it. Astronomers also use advanced imaging techniques to keep up with its motion. Instead of taking one long exposure, which would leave the comet as a blurred streak, they capture hundreds of short images and combine them using a process called shift and stack. This lets the comet stay sharp in every frame while background stars smear away, revealing delicate details otherwise invisible. The Hubble Space Telescope, orbiting far above the turbulence of Earth's atmosphere, has achieved some of the clearest and most breathtaking images of an interstellar object ever recorded, thanks to this same tracking technology. Radio astronomers face an even greater challenge. Their instruments require pinpoint accuracy, often measured in fractions of an arc-second, to capture the faint whispers of radio signals reflected by the comet. They must not only adjust for the comet's rapid motion, but also for Earth's rotation and a powerful cosmic effect known as the Doppler shift. As the comet moves toward or away from us at tens of miles per second, it changes the frequency of any radio waves it emits, much like a siren changing pitch as it speeds past. Without constant recalibration, those tiny shifts could drown out the signals completely. Despite these incredible challenges, astronomers around the world have united in one of the largest coordinated observation campaigns in history. Ground-based telescopes, orbiting observatories, and even skilled amateur astronomers are contributing to a continuous, global effort to monitor this interstellar wanderer. All eyes are now fixed on a single date, October 30th, 2025, when the comet will make its closest approach to the Sun. That day will mark the climax of its billion-year voyage across the galaxy, a brief but spectacular moment when a traveler from another star passes through our sky, and then continues its eternal journey into the dark. On that day, the cosmic wanderer will reach its perihelion, the closest point to our Sun, just 130 million miles away. That's inside the orbit of Mars, where the Sun's radiation becomes fierce enough to awaken the sleeping heart of this alien traveler. At that distance, the comet will endure nearly 3 times more solar heat than Earth does, transforming it into a breathtaking celestial display. The deeper layers of the nucleus, ice frozen since the dawn of another star system billions of years ago, will begin to vaporize, revealing materials untouched by time. These pristine elements, shielded during the comet's long journey through interstellar space, may hold the original chemistry of its birthplace, ancient signatures of a world beyond our own. As activity intensifies, its tail will stretch for millions of miles, glowing brighter and grander with every passing day. Scientists believe the comet could become visible to amateur astronomers with even modest telescopes, a once-in-a-lifetime chance for the public to witness a visitor from another star system. Yet, this beauty comes with challenges. As the comet draws closer to the Sun, it will sink into the blinding glare of daylight, making it nearly impossible to observe from Earth. For a time, its light will vanish into the brilliance of the Sun, and astronomers will have to pause their watch, waiting for the moment it reappears on the far side of the Sun in early December. During this critical phase, space-based observatories like SOHO, designed to study the Sun's outer atmosphere, might be the only instruments able to capture it. Their specialized lenses can block out the solar disk, revealing the faint shimmer of the comet as it dances through the fiery halo. At perihelion, gravity and heat will wage a dramatic battle. The Sun's immense pull will bend the comet's trajectory, slightly altering its path through the galaxy. Precise measurements during this encounter will help astronomers predict where this interstellar traveler will go next, once it escapes our system. The searing heat may also test the comet's structure to its limits. If it hides volatile ices like carbon monoxide or nitrogen, they could erupt violently, shattering parts of the nucleus or creating sudden jets of gas and dust. Such outbursts would offer an unprecedented look inside an object that was born around another star. For planetary scientists, this moment is the peak of discovery, a chance to see how alien materials respond to the energy of our Sun. By comparing this interstellar comet to familiar ones born in our own system, scientists may uncover fundamental differences in composition and structure, silent clues to how other solar systems form. As the comet swings around the Sun, telescopes across the world will lock on continuously, gathering data in a rare global effort. Each image, each spectrum, becomes a precious fragment of a larger story, the most detailed portrait ever made of an interstellar visitor in motion. Unlike Halley's or Hale-Bopp, which return after decades or millennia, this wanderer will never come back. Its orbit isn't an ellipse that loops around our sun. It's a hyperbola, a one-way path. Imagine throwing a ball so hard that it never falls back. It just keeps going. That's this comet. It will visit once, then vanish forever into the dark. Traveling at over 137,000 miles per hour, it carries too much energy to be captured by our sun's gravity. Instead, it will slingshot around the sun and accelerate outward, racing back into the endless night of interstellar space. After perihelion, it will begin its final farewell, crossing Mars's orbit in November, then Jupiter's in early 2026. By 2028, it will drift beyond Saturn's domain, where sunlight is too faint to sustain its glowing tail. Slowly, it will fade, a ghost of ice and dust gliding into silence. In about a century, it will cross the heliopause, the invisible border where our sun's influence ends and the galaxy begins. Beyond that, it will once again belong to the stars. During its fleeting visit, the comet will leave behind microscopic traces of itself, interstellar dust, a whisper of another world now mixed into our solar system's story. Our sun will have captured a tiny piece of another star, even as the comet itself drifts back into eternity. And though its course will bend ever so slightly from the sun's gravity, that small deflection could decide which star system it visits next, perhaps millions of years from now. This is a one-time encounter. Once this traveler departs, humanity will never see it again. Every observation, every image, every spectrum gathered today is a message from another world, carried across the galaxy, and now, finally, shared with us. The Atlas telescopes see a universe invisible to human eyes, a hidden cosmos filled with faint travelers drifting between the stars. While human vision can only detect stars down to 6th magnitude on the darkest, clearest nights, Atlas can reach magnitude 20, spotting objects 100,000 times fainter than the dimmest star we can see. To grasp that difference, imagine watching a single match flame. With your naked eyes, you might see it from across a football field. Atlas could detect that same flame from 3,000 miles away, the distance between New York and Los Angeles. This extraordinary sensitivity comes from a powerful combination of giant digital sensors, precision optics, and advanced computer processing. Each telescope collects light for 30 seconds per exposure, gathering faint photons that would be completely invisible to the human eye. Where we reset our vision every fraction of a second, Atlas builds its images patiently, stacking light from objects millions of times too dim for us to ever perceive. Its detectors also see beyond visible light, reaching into the near-infrared, where warmth itself becomes visible. This allows Atlas to spot asteroids and comets not just by the sunlight they reflect, but by the heat they emit. Even dark, cold objects that barely shine become visible through this extended vision. Behind the scenes, powerful software compares each new image with catalogs containing millions of known stars and galaxies. Anything that appears in a new position, even a single pixel of movement, is immediately flagged. Within minutes, the system identifies moving objects in real time as they glide across the sky. Atlas captures 4 images of every sky region, each 10 minutes apart. This gives it the power to see motion far too subtle for human eyes. A drift no larger than a grain of sand seen from 100 feet away. Special filters then enhance asteroid visibility, cutting out much of the atmosphere's natural glow and giving Atlas clearer, deeper views of space. Working together, the 4 Atlas stations form a single global network. While humans can only see one half of the sky at a time, Atlas covers the entire night sky every 24 hours. No object, no matter how small, how faint, or from which direction it approaches, can pass unnoticed. Atlas never blinks. It doesn't rest, tire, or lose focus. Night after night, its robotic sentinels watch the heavens with unbroken vigilance, scanning for the next visitor from the stars. The 4 telescopes, separated by thousands of miles, operate like a single living system, a network of mechanical eyes sharing one purpose. When the Chilean observatory detects a moving object, data instantly flows to all 4 stations. Within minutes, the others turn their gaze to confirm or dismiss the sighting. This rapid verification prevents false alarms from satellite trails or stray cosmic rays. And because their views overlap across different horizons, one telescope's fading glimpse becomes another's perfect vantage point. Together, they form a seamless relay of observation, immune to clouds, weather, or technical glitches that might interrupt a single sight. Each telescope adds its own strength to the collective intelligence, creating a global guardian that never sleeps, never misses a moment, and never stops watching the silent ocean of stars. The Hawaiian observatories stand in one of the most stable regions of our atmosphere, high above the Pacific Ocean, a place where the air remains steady enough to capture the sharpest, most precise images imaginable. Far across the world, the South African telescope peers into the cosmos from one of the driest climates on Earth. The lack of moisture there means no distortion, no absorption, just the pure light of the stars. And in Chile's Atacama Desert, perched high in the Andes, the skies are so clear that astronomers can detect the faintest cosmic whispers that would be invisible anywhere else. But what truly makes this global network powerful is not just location, it's time itself. As our planet spins, one telescope moves into daylight, while another enters its perfect viewing hours. When a new asteroid is spotted in the morning skies of Hawaii, observatories in Africa or Chile are already waiting to track it by nightfall. This seamless 24-hour cycle means no blind spots, no missed opportunities. All data from these stations flows together in real time. Sophisticated algorithms compare every observation, searching for anything moving too fast or too strangely to be a mere coincidence. If one telescope spots a high-velocity object, the network instantly alerts others to lock on and confirm. This coordination gives humanity the ability to track cosmic objects that would once have vanished forever into the dark. The system's redundancy is its strength. Even if one telescope is lost to bad weather or technical failure, the others keep watch. Together, they can still refine an asteroid's orbit, predict its impact point, and calculate when, or if, it might strike Earth. Every site is connected by high-speed, dedicated links, transmitting massive volumes of data across continents in mere seconds. Advanced compression systems make it possible to share the night sky in real time, turning individual observatories into one unified global eye. This collective intelligence does far more than just spot moving dots. By combining data from multiple telescopes observing the same object from different angles, astronomers can determine its orbit within hours, a process that once took weeks. It's a revolutionary step in our ability to monitor both cosmic visitors and potential threats. Night after night, this robotic alliance guards our world, scanning for the faint, silent wanderers that drift too close. Atlas is just one part of a vast planetary defense network, working side by side with NASA's Catalina Sky Survey, the Linear project in New Mexico, and the NEOWISE Space Telescope. Together, they form overlapping coverage of the entire sky, ensuring that no significant asteroid can approach undetected. Thanks to these efforts, over 90% of near-Earth asteroids larger than a kilometer have already been discovered, enough to eliminate the risk of a sudden civilization-ending strike. The warning times they provide scale perfectly with our ability to respond. A 2-mile-wide asteroid that could destroy the planet would be seen decades ahead. A city-sized one, weeks in advance. Even smaller, 60-foot objects are often spotted days before they reach our atmosphere. These discoveries align with the rise of real planetary defense technology. NASA's DART mission proved we can alter an asteroid's path with a direct impact. Europe's upcoming Hera mission will study that collision in detail, teaching us how to deflect threats more precisely in the future. And if deflection isn't possible, tracking still saves lives. With precise orbits, authorities can predict where smaller asteroids will land, giving time to evacuate specific regions without unnecessary panic. Atlas specializes in these last-minute detections, the small, fast, and unpredictable threats that might otherwise catch us by surprise. By scanning the entire sky every single night, it ensures that nothing sneaks up unseen. Behind this global vigilance lies an intricate web of communication and coordination. The Minor Planet Center in Massachusetts collects observations from across the world, calculating orbits within hours. NASA's Planetary Defense Coordination Office stays in constant contact with international space agencies, military networks, and emergency services. If a hazardous object appears, automated alerts can notify key decision-makers within minutes, triggering worldwide response protocols instantly, and the system keeps evolving. New telescopes are joining the watch each year, and upgrades make old ones stronger than ever. Soon, The Vera Rubin Observatory in Chile will transform asteroid detection once again, capable of finding objects hundreds of times fainter than anything seen before. It's expected to discover over 5 million new asteroids within its first decade. Meanwhile, the upcoming NEO Surveyor, a space-based telescope, will watch from above Earth's atmosphere, detecting dark objects invisible from the ground. Together, these next-generation sentinels will close the last gaps in humanity's defense against cosmic danger. But this story isn't only about protection, it's also about discovery. Astronomers now believe that at any moment, thousands of interstellar objects may be passing quietly through our solar system. Most remain hidden in the distant cold beyond Neptune, but as our technology improves, we'll begin to find them, one by one. The Vera Rubin Observatory will play a key role, scanning the entire visible sky every 3 nights, and revealing interstellar travelers hundreds of times fainter than any we've seen before. Scientists estimate it could find 1 to 3 new interstellar objects each year, each carrying clues from distant stars. Some will point back to their home systems. Others will carry unique chemical signatures, revealing the makeup of worlds light years away. Together, these discoveries will form a map of how material moves between stars, a cosmic fingerprint of our galaxy's grand design. And as telescopes become even more powerful, they'll begin detecting objects as small as cars, fragments chipped from alien asteroids, carrying pieces of other worlds through the endless dark. Each one a messenger from a place we may never see, whispering the story of a universe that never stops reaching out. The James Webb Space Telescope, along with the next generation of extremely large ground-based observatories, will soon open an entirely new window on interstellar exploration. Armed with unmatched spectroscopic power, these instruments will allow scientists to study visiting objects from other stars in breathtaking detail, detecting faint traces of organic molecules and exotic ices that reveal how chemistry evolves across different corners of the galaxy. Some of these samples may even carry biosignatures, the chemical fingerprints of life itself, preserved within fragments that drifted through the void for millions of years. To capture these cosmic travelers, specialized missions are already taking shape. The European Space Agency's Comet Interceptor will wait at the L2 Lagrange point, ready to launch at a moment's notice. When the next interstellar visitor appears, it will send small probes racing through space to meet it face to face, collecting samples, measuring isotopes, and uncovering secrets impossible to see from Earth. Meanwhile, advanced computer models are learning to predict where and when new visitors might appear. By simulating how planets fling debris into space and tracing their galactic orbits, astronomers are building roadmaps for interstellar arrivals. This could soon allow us to aim our telescopes not in reaction, but in anticipation, greeting travelers before they even reach the inner solar system. The pace of discovery will only accelerate. Freed from Earth's atmosphere, space-based observatories will search continuously, scanning every wavelength of light. Infrared sensors will uncover dark, frozen bodies invisible to optical telescopes, while ultraviolet cameras capture the gas plumes of active comets. Artificial intelligence will sift through the data, automatically identifying new interstellar objects faster than human eyes ever could. And so begins a new era, where finding visitors from other star systems becomes not a once-in-a-lifetime event, but a routine part of astronomy. Before 2017, our understanding of alien worlds came entirely from indirect evidence, flickers of light, subtle wobbles of distant stars. But when the first interstellar object streaked through our solar system, it gave us something we'd never had before, a direct sample of another world. The chemical signatures we've studied since then prove that the building blocks of planets, water, carbon dioxide, and complex organics, form the same way across the galaxy. Physics and chemistry, it seems, play by the same rules everywhere. Yet within those similarities lie subtle differences, isotope ratios, trace elements, and mineral fingerprints that tell stories of diversity among the stars. Some interstellar objects come from metal-rich regions, bursting with heavy elements. Others from the quiet, ancient outskirts of the Milky Way. Each one offers a clue about how stars and planets evolve in their unique corners of the galaxy. These cosmic travelers also reveal something profound, that planetary systems are not isolated islands, but part of a vast interconnected ocean of matter. Every star system ejects debris, comets, asteroids, and dust, into interstellar space. That material drifts for eons until gravity captures it again, seeding new worlds with the ingredients of life. It's a galactic exchange, a cosmic recycling program that binds the stars together. The diversity and motion of these visitors help map the structure of our local galaxy. Their arrival directions trace the invisible gravitational currents flowing between nearby star systems. Each trajectory adds another data point, another thread in the grand tapestry of our galactic neighborhood. But these objects also remind us of how much we still don't understand. The first interstellar visitor, that mysterious needle-shaped enigma, didn't behave as any rock should. It accelerated without visible outgassing, forcing scientists to rethink what happens to ices and minerals after millions of years in deep space. Later, the hydrogen ice theory helped explain it, showing how radiation can turn frozen water into invisible thrust, pushing a silent traveler across the stars. That fleeting discovery in 2017 was a wake-up call. We realized how unprepared we were, how easily a once-in-history event could appear and vanish before we even noticed. In response, humanity built Atlas and other all-sky networks, robotic guardians scanning the heavens every night, ensuring we'll never miss another visitor again. And in July 2025, that vigilance paid off. Atlas detected a new interstellar comet, active, glowing, and perfectly aligned with what our models predicted. Unlike its mysterious predecessor, this object behaved exactly as expected, revealing chemistry from another star, its tail sparkling with alien ices. It was a discovery that proved how far we've come, from surprise to mastery. Each of these discoveries expands our understanding of the galaxy's hidden exchange, of how worlds form, evolve, and share their essence across space. The same technologies that hunt these wanderers now protect our planet from asteroids, detect distant supernovae, and even inspire breakthroughs in medicine and AI. The search for interstellar objects has become more than science. It's a story of connection, because every rock that crosses the boundary of our solar system carries more than dust. It carries history. It carries the fingerprint of another sun, another world, and maybe, one day, another form of life. The first interstellar object showed us that the universe still holds surprises beyond imagination. The next will show us how those mysteries fit into the grand story of creation itself. And so, as we continue to watch the stars, we wait, because somewhere out there, even now, another traveler is already on its way, racing silently through the dark, heading straight for us. And when it arrives, we'll be ready.